Pamela.
Okay, thank you, Ross. Well, first, thank you to the British Columbia Geological Service for inviting me to the summer talks, and to Dominic and Ross for organization and putting all this together. Today, I want to introduce you to a workflow design experiment we conducted in York University back in 2019. It was pre-published in 2020, and now it's being fully published this year. It's based in a paper called Laser-induced shock and melting during LIBS analysis of ophiolitic rocks, an implication for sequential LIBS Raman workflows in planetary and terrestrial exploration. I am the first author, but I also work with Emmanuel Lala, Jane Fremantle, Mike Daly, and Alan Coyne. So basically what we do was understanding how LIBS can modify the geological materials that we were analyzing. What will this imply where we are performing other analysis? In our case, we did Raman and others. So why we should care? Because LIBS is increasingly paired with Raman spectroscopy in both planetary missions and terrestrial exploration. Currently today, we have an ongoing planetary mission on Mars, the rover Perseverance from NASA, which holds a SuperCam, which is on top of the rover. I don't know if anyone noticed or have seen the Perseverance rovers before, but they have a LIBS and a Raman combined with cameras as well in the head of the rover. And they are using those techniques to analyze samples up to 20 meters distance for LIBS. Also, another planetary missions traveling soon to Mars will be the ExoMars, which will hold a similar artifact on the combined instruments on the head of the rover. And for terrestrial exploration, well, we use it in mining, portable LIBS and portable Raman, more and more currently today. Because Raman is fast, non-destructive, and in situ, ideal for remote time critical environments. But LIBS is destructive and provides elemental compositions, including major, minor, and trace elements. And I will show you why LIBS is destructive during this talk. Raman provides mineralogical molecular identification when LIBS, during this experiment, we confirm modifies the target. And Raman might record a spectrum of different material. It's important and irrelevant for BC geology and exploration because we were working on the ophiolitic terrains, EOCG or copper gold system deposits, and drill core and full field work as well when we are logging or when we are exploring on the field, sorry. So our approach, it was a multi-technique workflow. So we moved from the macroscopic to the nanoscale using a set of 4 different instruments. So we choose samples. I'm going to explain more about the samples we choose and why we choose it in a few minutes. But the sample A was an isolite peridotite, and the same sample B was a basaltic with carbonates, a secondary carbonates. So we perform a petrographic characterization. Then we perform the LIBS analysis on the sample. We took it again to the optical microscopy. We map the craters of the LIBS ablation. Then we took it to the SAM-EDS instrument, electronic microscope instrument, to record the mineralogy or changes in the mineralogy in the sample, composition in the sample. Then we perform the micro-Raman spectroscopy in the area where we shoot the LIBS. I don't know if you can see my cursor, but so if this is the sample before we shoot LIBS, this is the sample after we shoot LIBS. And then in the SAM-EDS, here you can see the halo and the craters that LIBS will cause on the sample. Then we perform the micro-Raman spectroscopy in these areas to see if it was any mineralogical change. And I also integrate this with an atomic force microscope so we can actually map these craters on the nanoscale and know exactly the measurement and the depth of the craters. So we choose samples that can be planetary analogs. Why we do this? So when we study instruments or instrument techniques or methodologies for exploration in space, sometimes we don't have samples or we don't want to use samples like meteorites or samples that like the Apollo mission samples that are in Houston or samples from meteorites from Mars. Because some techniques can be destructive, so we can use analog samples. So these are samples that they are mineralogical and geochemical, similar to samples that can come from space to meteorites or the moon or Mars. So we choose a sample that was an ophiolite derived isolite peridotite that was relevant for terrains of IOCG style deposits, for example, in BC, in this case, and it's composed by silicates, iron oxides, copper, iron sulfides, and carbon-bearing microdomains. And then we choose another sample that is a plagioclase-rich basaltic lava with secondary carbonates. The composition was a bitonite labradorite dominated with carbonate-bearing veins that was analogous to Martian volcanic terrains and a carbonate-rich lithologies, for example, so ideal for ExoMars studies. The sample A is also very similar to some meteorites as well. So both samples combined can give us information of material behavior using LIBS and Raman when we are like analyzing in space, for example. And these are these images under here. Those are photographic images from sections like the mineralogy of the sample. So what was the research question we did to ourselves? Was understanding how LIBS modify rocks and what it means for Raman. So what is the size and morphology of the LIBS-induced alteration halo? So LIBS is a laser. Sorry, I haven't explained what LIBS was, but I assume everyone knew. So LIBS is a laser. It's a laser-induced blast spectroscopy. So basically, it's a very potent laser that we shoot to the sample. Will originate. It will evaporate practically the sample, and that the plasma of the evaporation will go back to the spectrometer, and then we can analyze which elements were in the sample. So how are minerals and texture modified by LIBS? Well, that was another of our questions. How does LIBS induce alteration affect subsequent Raman measurements? Raman is another instrument that is actually non-destructive. It's a light, basically. So it will reflect in the sample and will give us the information when the change of the electrons happen back on the spectrometer. And then what operational parameters minimize alteration and biases, and what guidance can be provided for robust sequential LIBS-Raman workflow. So those were our questions. So we produce a laser pulse LIBS in the sample. We create a shock thermal effect that was observable in the microscope. We create an alteration halo around the LIBS crater. And then we perform the Raman analysis along the sample. I'm sorry if I'm going too fast. Our two geological samples, in our case, came near Liguria region, northern Chile. They are from an IOCG sequence in Chile. So we study the petrography very carefully, and we define there was composed, sample A was composed by olivines, clinopersons, nephelines, oxide iron sulfides, carbon iron sulfides, and carbon-bearing microdomains. The planetary relevance, it was a mafic, ultramafic planetary crust, ophiolitic analogs, and correspond from alterations, iron-rich alterations environments. And the sample B was bitonite labradorite composition of pyroxenes, oxides, irons, and carbon veins, secondary carbon veins, and secondary alteration, analogs to, as explained before, Martian volcanic terrains, carbon-bearing lithologies, and ExoMars science target. For example, these are cross-pole and non-cross-pole images, photographic images from these samples when we were studying them. So the setup, the experimental setup, we choose a very potent ultra 1064 nanometers laser. This is the laser. We choose the distance of the laser so we can calculate a specific power of the laser that we want to shoot on the sample, and then we put the sample in this position here. So the pulse duration of the laser was 7 nanoseconds, and we used 10 hertz of repetition rate with a pulse energy between 5 to 100 millijoules. That's not correct, it should be percentage. And a beam spot size, that is what the laser can do. And a beam spot size of approximately 100 microns. And then we use a HL spectrometer for this study. And we acquired the data with the under-solid software. We perform a single pulse LIBS laser per crater we created with the spot spacing in 200 microns. So we were pulse 1, we will shot in the sample 1, and then we will move 200 microns, and we will do it again, and we will repeat. So we did this many times in different laser powers, because we also want to see if we were shooting the laser with, for example, 5% of the power of the laser, or 20% or 10%, if that would create any difference in the changes in the mineralogy that we were observing. So this is repeated. I don't know why I put this one again. So sorry. So when we perform this analysis, we determine the spectral characteristics for sample A in the LIBS spectral. It was strong in magnesium, iron, calcium, and silica, with features prominent of iron, titanium, chromium. And we detected nickel, and copper, with also sodium and potassium for the feldspatoids and accessories. For example, B, we detected strong calcium and aluminum lines, of course, because we were present plagioclase. I explained that was a basaltic sample. We also saw magnesium, iron, and titanium consistent with mafic basalt, sodium and potassium from the plagioclase present in the samples, with enhanced calcium and carbon from the carbonate veins. So the LIBS data was concordant with the petrographic analysis of the samples, also the analysis, what we saw in the hand samples. So LIBS detected a wide range of elements in both samples, and the spectral reflected major mineralogy from mafic, ultramafic in sample A versus plagioclase-rich basalt carbonate from sample B. We traced some minor elements, for example, nickel, copper, chromium, and magnesium. And the trace elements we also detected was copper, zinc, barium, strontium, lithium, and rubidium, in between others. So those all were observed with LIBS. In every different power energy that we shot with the laser, we were able to observe. So the blue, black, and pink lines are different powers of laser in this case. And for example, one is 5%, 10%, and 20% of power laser. So we detected all of them in the different power lasers. What we observed during the optical petrographic study for the craters of laser impact is for 5%. We have a diameter of crater of 200 microns, but the halo, so the halo is alteration area observable around the crater. It was 400 microns. But when we went to 10% of laser power, we observed the same diameter in the crater, because the diameter in the laser didn't change. But the alteration halo was up to 600 microns. But even when we moved to 20% of laser energy, we did increase a little the diameter, like it was more rock melted, basically. We increased the alteration halo up to 200. It went even up to 1,000 in the more carbonatic bearing samples, as you can see here, as 800, but it was up to 1,000. So it was observable even in visual that LIBS power was also impacted in the way was altering the sample from 5% to 20%. Then when we do the SIM-EDS, and these are improved images with AI. So I took the original images I have from SIM-EDS, they were a little darker, and I use AI to improve them. So they look a little weird, but they are the real data. I assure you, they are the real data. So we did see that from 5 to 20%, it was an increase in distribution of some of the elements that they were more volatile in this case, in the reposition around the halo of alteration, as you can see on this image, for example, calcium or sodium, for example, A and B. So when we were like increasing the energy from low to high energy, what we were observing was this increase in the halo of alteration in the samples. It was no linear halo growth, but it was a significant increase, especially for the basalt with secondary carbonates in the samples, as it was more susceptible, we assume, that from the more crystalline basic composition sample. So that was visual, and that was observed as well in the SIM-EDS. These are real SIM-EDS images, but they are improved as well with AI. I'm sorry about that. So what I wanted to show in here is if for the lower energy around and outside the area of impact, there were fractures in the rocks. They were observable in the SIM-EDS during the studies. For medium energy or 10% of laser energy, what we have, it was some redeposition of material that was also mapped and observed with the atomic force microscope. For the high energy, up to 20% of energy with the laser, what we have is not only the fractures and the reposition of material, if not also like flows, like it was like a flowing of material. The sample was recrystallized completely and was flowing as lava will flow from a volcano, basically. So we created shock fracturing, we created melt generation, and with material redeposition, splash of material redeposition around the sample, surface restructuring, and alteration beyond the crater margins. So these are images of the atomic force microscope. This is topography and 3D and 2D heat map. So I wanted to perform this study as well because I wanted to know how deep on the sample these craters will go and also the alteration halo. So what we saw is for samples that they were in the 5% of range energy, the crater will reach, this is not correct, sorry. The crater will reach up to 1.5 nanometers, nanometers, when in 10% and 20%, they will go up to 2 nanometers, which it was recorded and I was observed before in other studies. So it didn't depend much on the laser energy, how deep it will go on the sample. It's always 2 microns, no 2 nanometers, 2 microns, between 1 to 2 microns. What happened after when we conducted the Raman? So when we used the micro Raman and we mapped it around the halo and around the crater, so these each different color is a different energy laser. It was from 5 to 20% from the bottom up. We found that especially in the carbonatic bearing samples, we generated majorite. So majorite is a mineral, a granite, but it can be generated in nature in very deep in the cortex, but and it was not present in our sample, but we actually created that mineral or the presence of that mineral with LIBS, when we recrystallized it, the mineralogy with the sample, which was very interesting. And also we recrystallize some iron to hematite that was not present in the sample before. So what this actually mean? Depending of the energy on the laser, we have different sizes of the crater, but the depth of the crater was the same. Depending of the energy of the laser, we have bigger halos of alteration. But regarding of this, the mineralogy will also change after LIBS. And what this means, especially for planetary exploration. So as I explained in the beginning, LIBS and Raman are incorporated in the Perseverance rovers. And when we are shooting LIBS and then we are using Raman to analyze in the same area without actually knowing that we change the mineralogy, we are changing the complete geological story, the history of the sample. For example, in our case, our samples belong to an ophiolitic sequence that was a basic sequence. And after LIBS, we have a continental, very deep in continent samples. So we basically changed the tectonic history of this sample when we shoot LIBS and then we perform the studies. So this experiment that we performed in the lab was very important to understand the order. Sometimes we have to use the instrument, the way we are analyzing our samples, why we're doing it. So as I already said, sorry, I went so fast. So we use LIBS. We perform a physical change in our sample and geochemical and mineralogy change in our sample. We saw it in evidence through Raman, CMADS, and atomic force microscope. And when our synthesis and our conclusions were when we are using these techniques of analysis, which will be the better order of the instrument analysis in the lab and also on the field. So recognizing and accounting for the hiding footprint of LIBS is essential for robust planetary science and also for on-Earth mining exploration. LIBS modifies far beyond the crater of the sample. Multiple processes are at play. In our case, shock, melting, redeposition, and mineralogical change all contribute to when we analyze the samples after LIBS. Carbonate is strongly affected, especially in sample B, we saw this. Multi-technique is essential during exploration in planetary or on Earth. Context is critical as well. Instrument parameters like lithology and sampling strategic control of the footprint. An implication for planetary science, the analytical footprint is far larger than the crater and must be considered in data interpretation and mission planning. So I don't know if anyone has questions. Maybe I went too fast. I can go back to the images. I can't hear anyone. Sorry.
Yeah, we all muted ourselves, but thank you, Pamela. It was really good.
Oh, okay.
Yeah,
okay.
we have lots of time for questions.
Okay. Yeah, I wanted to do it in half an hour, but maybe I went too fast because it's only 25 minutes. I'm so sorry.
Oh, that's good. That's good.
Okay.
Any questions?
I'm going to go out from here so I can see.
I have a question, Pamela.
Yeah.
Maybe you said it in the intro, but what's the context of using the LIBS analysis in general, like for Perseverance? Why are they doing that in the first place?
Well, LIBS can give you elemental composition. Let me see if can you see my screen, right?
No, you stopped sharing.
Oh, I stopped sharing. Okay, let me go back and share my screen again. So here. So now, can you see my screen now?
Yeah.
Okay. So LIBS here. LIBS give you elemental composition and a broader range of elements can be analyzed with LIBS. So you will know that you have aluminum, you have magnesium, and even you can sometimes know the isotopes if you use a specific LIBS techniques. So you will know your elemental composition in a point in the sample. It won't give you gold, but it can give you copper, as I had shown you, or magnesium or nickel. So if you're studying on a specific deposit, for example, in mining, let's say, and you're looking for a specific elemental composition in your sample, no mineralogy, elemental, and you say, okay, if I have this as an association, nickel, chromium, and iron, you are in an IOCG. So you want to look for those elements. When Raman give you mineralogical composition. So when Raman, you will see minerals. Where is Raman here? So you will see, oh, I have magnetite, I have hematite, I have pyrite. It won't give you the elements, but it will give you the minerals. So what happened when we shot our LIBS will change the mineralogical composition of the sample, because we generate magnerite and we generate hematite. Hematite, yes.
I got it. Thanks.
Yeah.
Yeah, I've got a question. It's really interesting research. Fascinating.
Thank you.
Do you get a percentage of an element that's there? You just simply detect that a element is present, or do you actually get a percentage of how much of that element is in a certain volume of rock?
Well, the instrument itself, the laser and the Raman, can quantify, but with AI today, they are generating these softwares that when you're mapping in an area, for example, you're using LIBS to map in an area of a core sample, you can quantify. So the software will quantify for you. But the instrument itself, it cannot quantify. It would just give you a spectral information, like here, like you are seeing here in the presentation. I'm showing you. It won't quantify. But softwares today, they are being built to quantify. So these companies that they are offering core logging in these machines, they are using these softwares to quantify. They're still improving. A few years ago, I saw one in Australia. It was very interesting what they were doing, but I noticed that they need a lot of improving. The other problem is these companies, when they are running LIBS and they're mapping LIBS over core sample, for example, I just show you how LIBS evaporate the sample actually and recrystallize the whole sample. So if you want to do that, it's okay, because when you shot LIBS, the data you have that point at that very moment is the exact data of the sample. But then after that, you have to probably polish that sample again up at least 2 millimeters, so you can clean all that affected area and then go again. But then if you're working in carbonates, for example, well, you know that LIBS can affect a broader area of the sample. So maybe you want to clean up to 5 millimeters at least of the core sample. For example, people that works in deposit that they have carbonatic veins. So you want to clean better your sample, or you just leave LIBS for the very last and perform all the other non-destructive analysis before. Sorry, you asked about the quantification and I went.
Well, I'm trying to connect this really high level, microscopic analysis to just a general analysis, chemical analysis of a core sample. So what we do is we send core into an analytical lab, and they come back with how much gold's there, how much copper's there, blah, blah, blah. But this is taking that light years beyond. That's the way I'm translating this, that you get extremely fine information. And
yes,
so that's essentially correct?
Yes, because this is how we do in planetary exploration, how we work in space. Because when we send something, for example, the Perseverance that is on Mars, we are analyzing, we have not much energy and we are analyzing point by point in the samples. So every little information we can get from the samples is very important. And we have to be sure the information we're getting from these samples is correct, even when there are very small areas up to 500 microns or less. So we have to be sure that the information we are gathering from the samples is correct, is 100% correct. When you're working in mining, it's a different context because you have access, you have the energy, you have access, you have the instruments and everything. But nevertheless, however, as I just explained, when you're using core, for example, and you're running core in these new machines that they are running LIBS map, they say LIBS maps, and they are running LIBS over the samples. The lasers are generating all these changes in the mineralogy of the surface of the core. So if you're going to use another instrument on top of that, as per example, Raman or micro-XRF, or any other instrument after LIBS, you're not going to be in the same surface. You're not going to be obtaining the correct data. You're going to be obtaining the elements that they have been created after LIBS. So you have to clean that core. Very simple. You clean that core up to 2 millimeters. So you basically repolish that core, and then you analyze it with the other instrument. Or if you have the option, just leave LIBS to the very last. Also, the scales of work. LIBS, I show you, LIBS can be like a point in a rock, or it can be a map in a whole core. So the scales of work can change with the same instrument. So you can change the composition in a very small hole that you produce, like in our case we did for our experiment, because it didn't have sense to do it in a full core. But if you use LIBS and you produce 1,000, 10,000, 100,000 holes, when you're mapping the core, you will create the same. You will be changing the mineralogy because you're blasting the sample.
Have you got any mining companies that are funding this or interested in using it, or what is the situation with mining?
With LIBS today,
Yes,
it's being used. They have created some hand LIBS.
Can you tell us what mining companies?
I don't remember them. Oh, I know. I don't remember. I don't know. Maybe probably all of them. I don't know. It's very common. It's very handy actually. LIBS hand tool in the field. I show you an image in the beginning here. This is a real one. This, you see the hand here? This is a LIBS. Yeah, it's very handy when you're in the field. Here as well, portable LIBS. It's very handy when you're in the field for use. Of course, when you're in the field, you shoot a place, and then you won't shoot Raman on the same place. In our case, in our planetary missions, as we are pointing with the head of the Perseverance, we were probably shooting at the same time, the same place. So the only thing it was need to do was just change the position in the workflow where we're going to use LIBS. Okay, leave LIBS to the end, not in the beginning. For example, I work with physicists, engineers, and they say, oh, because I explained to them it's better for the geologists, we have the clean area of the sample before analysis, but we cannot do that in Mars because we are not there with our geological hammer to clean the sample. But they say, oh, we can clean it with LIBS. That was when first this question arose on my mind. Oh, wait, you're cleaning it with LIBS and then you're shooting Raman? No, that's not a good idea. So we perform all this experiment actually to check if LIBS was changing, producing a change in the sample, because I assume it was a blast. It was blasting the sample. It was evaporating the sample. So I assume it was, and it was. So we show it with many different instruments, not only one. So we told them, no, don't clean the samples in Mars with LIBS. Just shoot Raman first and then shoot the LIBS. And that was all. But when you're in the field with this type of tools, it won't be a problem. But when you're running core, especially when you're running core in these companies that offer that service, that you can put the core and it will go on the machine and perform X-ray and many other analyses at the same time, we just tell them use LIBS at the end. Or if we don't have that option, you run LIBS and then polish the sample and then run the rest of the analysis, that they are not destructive. So it's important to understand that LIBS is a very good instrument, a very good technique for elemental analysis in the field and in the lab, but it's a destructive analysis, so it will change even the composition of the sample in the area of analysis.
Could I ask a follow-up question to that? So, when I don't know when you recognized that the order of things wasn't really conducive to best scientific practice, but how would this would this have an effect on sort of vintage data that was collected from Mars decades ago? Is it possible that you would have missed, say, hydrous minerals as you were analyzing them for mineralogy, so missing things like serpentine or different hydroxides?
Well, theoretically, yes. I haven't checked the data myself, and I won't do it because I'm currently not working right now on that specifically. But yes, and today they are applying a new technique. I read on the news that they realized something with another instrument as well, and they were missing some very important minerals, so and molecules, I'm sorry. So they are changing some of the way they were using some of the instruments. So we are in a learning path. So it is possible that we were doing it incorrectly 2-3 years ago. Yes, it's possible, but the good thing is researchers like this can realize that was happening, and we can change it in time.
So that's,
See that?
he had his hand up.
Oh. Yeah, if anyone online wants to ask a question, you can unmute yourself and go for it.
SG. That is, oh, it's everybody.
I don't see search.
No,
Russ?
sorry.
Yeah, thanks, Pamela. That was really interesting. One quick question. I think you've kind of answered a little bit, but how do you approach data collection on planetary experiments versus on Earth? Are there any major things that you have to do differently, or is it basically the same?
Well, it's basically the same. The difference is remotely. So the instruments are in a, for example, in Mars, they're in a rover. So you have a workflow, and the rover, you tell the rover each, I guess, not me, the scientist will working, will tell the rover, move 10 meters or 2 meters northeast, that direction, stay there, and then you observe first with the cameras, then you choose a rock that is of your interest in, and then you start using your instrument. If there is in distance, you will use Raman and LIBS. And if there is the sample that you want to collect is under the rover, you can drill, collect the sample, and then perform the respective other analysis in the rover. So when you want to explore in space, you try to choose instruments that can give you the most of the information. For example, LIBS, as I explained, give you the elemental composition, and Raman, the mineralogy composition, just so you can have a broader spectrum of data that you can do geology, understand the geology of the area you're studying. And also we have cameras, so there is cameras in the instrument, so you can, in the rover, so you can see where you're, the rock, if it has any geological characteristic. For example, now they are showing rocks on Mars that they look like the deposit of dunes, can be maybe wind, it can be water, and then analyzing them. So I don't know if that was your question.
Kind of. I was thinking more like
In the data.
special
the data,
considerations,
yeah.
like the instrument gets dirty all the time and contaminates it, or it works easier in space because there's no atmosphere. You know,
Well, it depends where you are. The Mars is a problem because there's winds and it's powder, powder everywhere. And then you cannot clean the area now with LIBS because we know we were changing the composition. The moon is a problem because the regolith of the moon electrocharged. So the particles, because the moon doesn't have an atmosphere and is actually little outside, it's not very well protected by our electromagnetic field. The UV radiation of the sun. So the bombardment of sun particles charge the regolith in the surface of the moon and make it levitate by electrostatic charges. So it moves and it gets stick to everything. So that was a problem the Apollo astronauts were having. I don't know if you have seen images of a photograph of how the suits, the white suits, were all covered on the regolith. Because this was happening over millions of years, the bombardment of the sun particles in the regolith. The particles of the regolith, they can be very fine, extremely fine. So they get into everything. And it's a problem for the instrument itself in the moon, as they will get inside and everywhere, and they are very erosive because they're silica, basically 100% silica. So they are very erosive as well. And in the surface of asteroids, with a problem, some asteroids are rubble pile. So it can be very fine material because of millions of years of bombardment and impact. It's called space weathering, that erosion that happens in space. And also you have big blocks. So when you are collecting samples or analyzing samples, it's difficult because you have these materials in the surface. But whatever analysis we can collect, even if it is not, it's a surface of a block and is covered with some of the finds of the asteroid, is important and it can give you much information. That data will be spectral data in the case of LIBS and Raman. Then we also can acquire thermal data, electroconductivity data, radar data in space. For example, the Hera mission that is flying now from ESA is going to acquire some data after the impact of the DART mission, NASA DART mission, in the Didymos asteroid. And that data will be very important. So we are working in between scales as well. So we're going to acquire electroconductivity and thermal data from the surface of Didymos. And you can analyze some meteorites that have similar composition of that asteroid. If you want to know how we don't know that, I can explain. So we can analyze these meteorites in an atomic force microscope in the nanoscale. So we analyze the matrix, for example, of the meteorite and some of the chondrulas, if there is the case, has chondrulas, or some of the carbonatic veins, bearings, if they have them. So we analyze it and then we extrapolate this to the macro scale with the satellite that is flying and acquiring the data. And we can do this. We can work in between scales as well.
Oh, fantastic. That definitely answers my question. Thank you.
Okay.
I'm interested in these hand instruments. Got a few questions about that. Do you know roughly what they cost?
I know the price from a few years ago. I don't know the price. I think it was $20,000 a few years ago. The LIBS, I don't know today the price, to be honest. The LIBS we use in the lab, this is a different LIBS. So this is a hand LIBS that you can use in the field, correct?
Right, yeah.
So it's not the same of having these LIBS in the labs. This is one of the most power LIBS that you can have. So
yeah, that leads to another question: is how much power does a hand unit take?
So
you only have battery power, right? And
yes, but you can choose the power you use of the LIBS. Of course, the most power you use, the faster you run your battery. But you can set up. I don't know if the people using the instrument knows that. I will do a 5% or 2% even of energy power. Or I don't know if the company has a preset the software to use it at 2% so it won't run the battery so fast. I don't know that. That will be an interesting question for the company to make. But if I am using that LIBS after my experiment, I would just do 5% on the field and no more of that, especially if I'm working in a carbonatic environment, because I know that I will alter the sample or the core. For example, if you're analyzing, you're logging your core, and you have carbonatic veins, and those carbonatic veins can go from millimeters to meters, right? So you have millimeter or centimeter carbonatic veins, and you're using LIBS in your core, and then you grab the same core and you send it to the lab, or you grab small samples of your core and you send it to the lab. Well, then you have some data that will be interesting because it wasn't there before, right? Maybe it won't be representative enough to give it any importance, but I don't know, maybe you were shooting the whole vein and then you send it to the labs, and then you will have, oh, why have granites here? It shouldn't be here, right? So so I would personally use 5% energy, but I don't know, maybe it's preset. There was one in UBC. I went and checked. I don't remember. Maybe I have that information. I can look for it. I don't remember if it was preset or not.
And my last question with these hand units, safety aspects. I mean, I envisage these things, if you hit your arm with it, you're going to burn a hole through your arm. Is that being a bit extreme? Or?
No, it's extreme. You won't burn a hole into your arm. You'll just make a small hole in your skin. No, just kidding. No, but you have to use safety glasses, lenses. They're like orange lenses, and you cannot don't shoot the laser to your eye, because then you will lose your vision. That's for sure. Don't do that. And when you buy the instrument, it will be in the information. It will be everywhere, like wear your glasses when you're using it, and don't shoot to your face or anyone else's face, of course.
Right.
But this is a class 2, maybe 1. This instrument here, this is a class 3. So there are 5 different classes of laser, 1 to 5. 5, for example, are the ones being used in military. 3 is the one we use in our labs most of the time.